If you think using atomics is easy, you are either jaded, one of 50 people in the world, that's a generous idea, or not being careful enough. This does not mean only 50 people in the world should use atomics. Many more can, and I'm working hard to have atomic smart pointers, which I'm not going to show much about today, but once you get those, it'll be even easier for mainstream programmers. But it's one of those things like people using a chainsaw. Yes, lots of people should learn how to use a chainsaw and can use one effectively, but if you get too comfortable with it and you don't respect the tool, bad things will happen. And this really applies to lock-free programming as well. Let's begin with why we want to use lock-free programming, because I'm going to talk about this a bit on Friday in the Back to Basics talk, but basically we don't want to use complex or advanced tools just for fun. Unless, it's a home project, a side project, we're experimenting and learning, that's fine. But in production, please be conservative. Use a tool when you know you need it, no premature optimization, and that applies to lock-free programming because it is inherently about optimization. You are trying to get better concurrency or better scalability, usually both. If you are not trying to get that, you have very little business trying to do lock-free programming. Because unless you're playing with it, why are you going to use the more advanced, more difficult to use tools? But if you do want better concurrency and scalability, you can often get them with atomics. Now, why do we want this? In your algorithms and your data structures, if you have blocking or contention or weighting, often we can slipstream work, and that will help us to allow more work to happen at the same time. And we also want to avoid some of the troubles with blocking or locking. And that's as shown on the screen. If you have your typical lock-based code using our nifty lock guards, which you should be using, never call.lock directly, this ensures you'll unlock exceptions safely. This code is so much better than if you call lock and unlock explicitly, but it still has pitfalls. It can still deadlock. It can deadlock with itself if mute table 1 and mute table 2 are parameters and two different calls on two threads happen to pass them in different orders. You have to worry about erases. Did you remember to lock, and did you remember to use the right lock? Because by default, if you forget to take a lock or you take the wrong one, what are the semantics by default? Program compiles and appears to work, and you probably ship it. And unless you're lucky and get stress testing, or you have a really bad race window that just manifests right away, you'll get problem reports from the field that are hard to diagnose. Also, simplicity versus scalability. If you're using locks, you really want to be very fine-grained. The problem is, the finer grained you are to get better concurrency and scalability, the harder it is to use locks, because the easier it is to use the wrong lock. Forget to take the right lock, get them in the wrong order. On the other hand, if you just take one big global lock for all shared state in the system, you'll never take locks in the wrong order. You may forget to take a lock, but you won't ever take the wrong one. It's simpler to deal with, but doesn't scale for beans. So there's this tension with locks between simplicity and scalability. Lock-free is not a panacea. Transactional memory hopes someday to be, but lock-free is not a panacea, but it can help us with some of these things. Important assumptions. I'm going to say these once, and then I'm going to assume, let's just assume I say this on every other slide for the rest of the talk. You've already measured, and so you know it's worth doing what you're about to do, which is optimizing using sharp tools. And once you have written it, this is actually important. I've fallen in this trap. You will if you have not already. If you then write your nice lock-free algorithm, and you think, okay, I'm keeping my producers and consumers apart, I'm padding, I'm doing all the right things, therefore it's better, then you measure again, especially compared to the previous one. Half the time you will find you're not better. Sometimes you can fix it, sometimes you can't, but it is not obvious where your performance goes. So I'm assuming you've measured to justify using the tools we're about to describe, and that once you've used them, you will measure again and regularly. That's just good discipline. Used to be great that a lot of us could get away with writing single-threaded code. Those were the days. Unless you were in those few people who were using Craze and other HPC kinds of environments, it was great just to be able to use a single thread. You don't need to lock, you always know what it does, especially if it's a single application and you own the machine, but for DOS. So once we have multiple threads, we have synchronization, especially if we have mutable shared state. So we talked about locks, and it is very useful to think of locks as traffic lights. Anytime you go to an intersection, that's a piece of shared state. You do not want two threads running amok through it at the same time. Sometimes you see that happen on COPS. Sometimes it works, sometimes it doesn't, right? So what do? We put traffic lights on. A basic mutex is very much like a basic traffic light. It's green this way, red this way, and then after a while we go green this way, red this way, or whatever the opposite is, and we cycle. Sometimes it seems fair, sometimes it's not fair. That also has an analog in locks. When you think about things like reader-writer locks, you might say, oh, that doesn't apply to traffic lights. Oh, sure it does. Left turn green arrows, right turn green arrows. I know that if I'm turning left only, that those guys can turn left too, and that others can turn right, going the 90-degree different way. Very much like a reader-writer lock in many respects, because we're optimizing certain kinds of flows. What we're mostly going to talk about is building cloverleafs. The idea is, instead of having that shared state that both are going through at the same time, is you build a bridge. You separate it so that usually the traffic going in different directions doesn't actually touch the same state. This would be uninteresting if that was all there was, because they have to communicate sometime. If the guy going this way puts an item in a queue, you want the guy going this way to eventually see it. That would be nice. Otherwise, the system isn't very interesting. So how do you communicate? Well, the traffic going this way, instead of using a piece of shared state, they elevate, and then you try to build these cloverleafs, build these ramps, so that traffic that was injected going one way can merge with the traffic going the other way without losing too much speed, and merge so that it's not like those stupid mergers that you all curse at, that don't give you room and you smack the side of the car and lose paint or share paint, but you want to line up so you're in the gaps in the cars. All of this has direct analogs with lock-free programming. And when you get that merge wrong, a lot of it's going to be like you're sideswiping cars or sideswiping data. So we're going to look at a lot of these. I'm not really going to go back to these metaphors very much, but it's very useful, at least I've found that, to think of the kind of synchronization we're doing in these terms. So we're going to look at our basic tools, and then we're going to go through 3 examples over the next 2 hours. So the way this is structured is the sessions are 1 hour long, and there's a 15-minute break in between part 1 and part 2 of this talk. So if I'm getting close to that but I don't already notice, let me know, hey, it's break time. And we'll take a pause, come back 15 minutes later, and continue to cover this material. A good rule of thumb for most talks, technical talks, I found, is 2 minutes per slide. We have 2 hours. I have about 60 slides. Last night I added 30. They are hidden behind the final questions slide, so if we get there, I think I can get through those 30 slides in about 20 minutes without rushing, because there's a lot of duplication there. But if we get to that part with 15, 20 minutes to go, we'll go to the bonus slides and it'll look like I meant it and had planned it, and this is a bonus, and otherwise nobody will know because I didn't just tell you this. The 3 examples that are on the official agenda: double-check locking, just to get our appetites whetted. That's only going to take about 3 minutes. Producer-consumer variations using locks and atomics together, and then fully lock-free. And then a singly linked list, how hard can it be? I just love those sections, the how hard can it be? Let's talk about fundamentals. Here are the tools that we're going to use. The first thing is, always think in terms of transactions. You will do well in programming in general to think of your system, your program taking the system from one valid state to another. Every member function is conceptually a transaction on the object, right? Because the invariants hold at the beginning and end of the member function method, if you're from other languages. And in the middle of it, you may be in some halfway state where you've partly updated the object, and that's okay. So think of each member function as a transaction on the object. Think of every locked region where you go lock, unlock as a transaction on the shared state. This is a good way to think, and in particular with lock-free programming, the way to think about it is that we're going to use atomics, which are these little synchronized variables I'll show on the next slide, where we're going to do all sorts of work and make it visible to the universe with a single atomic write instruction. You say, well, how could I possibly make 1 million updates visible? Think atomic pointer. You can build up the most complex graph you ever thought, and nobody else can see it in your program until you publish pointer to root, and suddenly it springs into existence for them. Very useful technique, and that's why almost all uses of atomics are for things like booleans and integers and for pointers. and make sure that updates don't interfere with each other so we're not sideswiping. So here is the fundamental tool. I talk about atomics. In the C++ standard, it's called std atomic of t, and there are some type defs for it. The semantics are that each individual read and write from that atomic variable is indivisible, is all or nothing. And they're also ordered, and really, you don't need to know most of the rules. If you want to know the rules, I have a 3-hour talk that's available on Channel 9 that talks about, for a whole half day, about atomics. It's entitled Atomic Weapons, Atomic Angle Weapons. Sorry, I couldn't resist. No, sorry, didn't want to resist. And the C++ memory model. You will know more than you ever wanted or needed to know, but is interesting and good to know if you look at that. I will assume you know the basics of that, but all you need to know is it's indivisible read or write, and nothing freaky will happen if you just reason about it in source code order. Most of the details of the memory model in atomics that I cover in that talk and that people agonize over in standards for years are to make that illusion true for you. So the short version is we did the work. Don't use the memory order parameter, just use default atomics, and you can actually reason about your source code as though the reads and writes were indivisible. There's one special instruction we're going to see. It's a family, because there's exchange, and there's also compare exchange. But compare exchange is the interesting one. It says, for a given atomic variable, all in one operation do what is shown as pseudo source code here on the screen. So this is not actual source code, because it really maps down usually to a single key instruction, maybe an instruction sequence with a single key instruction on your processor. You don't need to know that, but it's as if you did the following source code. For my atomic, if its value is expected, atomically change it to the new desired value and return true. And if it wasn't equal to expected, return right into expected the value that you actually found there and return false. A very good way to think about this is when you say, my atomic dot compare exchange expected to desired. A very good way to think about that in almost all cases is you're asking, with that bool result, you're asking, am I the one who gets to change this atomic from expected to desired? That's the way to think about it. So we'll use atomics in that operation in particular. A few notes about it. Can you have atomic of some big pod? Yeah, you can do that. Now you might say, well, how's that possible? I know my x86 or my ARM chip doesn't have 4K memory compare exchange. It doesn't need to. The atomic of big struct will insert a lock under the covers, a spin lock. And if you're thinking, oh no, deadlock, don't worry, it doesn't matter. It can matter for performance, but never for correctness. That can never deadlock, because that's a leaf level lock. You never, while holding that, try to acquire anything else. Leaf level locking is always fine. Deadlock only gives you a problem if you're holding a lock and then might try to get another one. Leaf level locking is fine for correctness, but be aware of performance. Now the good news is I'm mostly including that for completeness, because mostly you just want atomic of bool, int, or pointer. But FYI, lock-free versus locked implementations can matter if you have atomic of something bigger. Initialization. We can argue about whether this is a defect in the standard, but remember that when you have an int I on the stack, int I semicolon, is that initialized? Sorry, what is its initial value? Anybody? Garbage. Trick question. Garbage, says Stefan. Rats, he's right. Okay, so if you'd put up your hand, I wouldn't have called on you, so you knew that, right? If you put an atomic of int I semicolon on the stack, its initial value is also garbage. This may be a surprise, but because you think, oh, atomic is a class type, nevertheless, just remember it's like an int. That's at least the way it's designed now, so just remember to initialize it. Interleaving, if you have an atomic and you say update it, like increment or something, or read or write, you're guaranteed that operation is atomic. But if you have two atomic operations, even if they're right next to each other, like read it and then in the next line write it, there's a window in there. Those two together are not atomic. Those are two individually atomic operations, and the window may be small, but basically in my experience on mainstream systems, Windows, Linux, x86, ARM, if you have a window that in source code looks like you're basically an atomic int read and then a separate right, or vice versa, right next to each other, that will be exercised roughly on the order of 1 time in 10 million or so under heavy contention where you're doing threads that are doing nothing but contending on that code. That's still too much, but it's probably enough to let you ship the code and think it's okay. So just remember that there's a little window in there. The way to think about it is in your source code, every time you see an atomic variable mentioned is an operation on it. So if you see it mentioned twice, so that's 2 operations on it, and there could be a window in between, so remember that. I'm generally going to use the term lock-free in its mainstream loose way, which basically means not using a mutex, although you can still write spin locks using atomics. To be very crisp, and academically, and sometimes this matters and I'll mention it, there are 3 major classes of lock-free algorithms. The strongest, the holy grail that you can sometimes achieve is wait-free. That means nobody ever waits. That is a wonderful story for scalability, because it means nobody ever waits regardless of how much other stuff is going on in the system. We love that. We can't always get it, but we love it when we can get it. This guarantees you basically system-wide throughput, plus nobody can ever starve. It's a guaranteed starvation-free programs. The next level down, if you can't quite get that, is called lock-free. And basically the way to think about this is somebody makes progress. If my thread has to wait, so it's not wait-free, my thread may have to wait, it's because somebody else made progress. Unfortunately, unless you have an idea of fairness, which usually you don't, I might be the loser forever. So, great, it's great for the world. Everybody is making progress, but in the worst case, pathologically, I could be the one who waits forever. So you can get starvation of a thread, but you can only get that if there's global progress. So this still guarantees system-wide throughput, does not guarantee starvation freedom. Third, this weakest but very useful in practice level of obstruction-free basically says, I will make progress as long as nobody else is doing anything. This means that if you have 2 threads doing something with that particular data structure, they may block each other forever and nobody gets anywhere. The good news is that's very rarely actually going to happen. So that's a live lock kind of situation, and usually we deal with that with some back-off algorithms, but it's unlikely to happen. Those live locks are very highly unlikely to happen or to be long-lived in practice. So this is actually a very useful level. It doesn't guarantee progress, but it does guarantee deadlock is not possible, though live lock might be possible. They won't deadlock each other, but they might live lock. In general, informally, lock-free means, yeah, one of these, but sometimes as we go, I'll be crisper about which level we're reaching with a given piece of code. Okay, that's our 2 basic tools, transactional thinking and atomics. How many of you have heard of double-checked locking? Who hasn't heard? No. Most people have heard of this by now. And in fact, you've probably heard that double-check locking is broken. You've probably heard that for many years now it has been unbroken. It's a useful pattern. And as Java and C# and other languages tightened up their memory models, this works just fine. The key is you want that key flag in this implementation, the p instance pointer, to be atomic. And then this all works. The basic idea is if you're going to, say, get an accessor to the global widget, you call the instance method, and it returns you a pointer to the global widget. Now, the first time you call it, you have to construct it. You don't want 2 threads constructing the widget. That could be an expensive operation. It could be incorrect to try to construct it twice. But you don't want to just take a lock every time. I mean, you could just say, take the lock, and if p instance is not null, return it. Release the lock. But that means for the whole lifetime of your program, you take the lock every single time you even want to look at the instance pointer, when the only thing you really need to protect is the construction to make sure it's done once. So the idea is we look at the instance pointer. So let's see if this feature works. We look at the instance pointer, and we do there, you see it mentioned, there's the name of p instance, so that's an atomic read. We then compare the result against null. If it is null, well, if it's not null, we just return p instance, that's easy. If it is null, now we're going to take a lock. This lock is only among the group of threads that might be concurrently calling instance the first time. Because maybe you're not the only one who is arriving to at the moment the door opens and asking for the instance. And here what we do is we make sure that we take that lock. If we then check that p instance is still null, why? Because if more than one of us got there at the same time to be the first to ask for instance, somebody else might have got the lock just ahead of me and already done all this work. So this second test is just in case there's multiple of us trying it concurrently at the same time. We check it's null to make sure only one of us actually creates the widget. We do that, then we release the lock, and we return. So that's a double-checked locking because we read p instance here, and then we read it again here. This is correct as long as p instance is an atomic widget. All the times you heard about double-checked locking being broken was basically about that atomic being missing in C++, or that volatile. In Java, it's called volatile, not like C++ volatile. In Java, volatile being missing there.
And as long as your compiler doesn't reorder the construction of the widget on the heap.
And as long as your compiler doesn't reorder the construction of the widget on the heap, which it won't do because you said atomic. Every article that you have read, including by Scott Meyers, Andrei Alexandrescu, and others about the double-check locking pattern is broken, and all the deeply weird things that can happen boil down to this simple fact. If you don't write that atomic, you have a race condition. Race condition means undefined behavior, and then you can write an entire set of articles about all the possible undefined behaviors there could be. If you write atomic there, there's no race condition because your shared variable is atomic. There's no race condition. Article goes poof.
I still don't see a sequence point between the new widget construction. Like, why can't we allocate a block of memory, publish it to p instance, and then new widget? Right?
So the question briefly is, well, couldn't you still get some unfortunate reordering? I refer you to my atomic weapons talk, which goes through in detail about acquire and release fences and why this works. In particular, the atomic variables are known to the compiler as special variables that can be used for inter-thread communication. Just like mutexes are specially known to the compiler, they implicitly have memory barriers. In particular, when you read from p instance, that is an acquire barrier. Code cannot be moved up across it. If you write to it, such as you do in this line here, that was a water bomb. If you write to it like here, that means new widget has to happen. Then in source code order, you do a write to p instance. That is a store release. That is a release write, which means you cannot move any of the operations to write the constructor writes if widget down across it. Anybody who sees the non-null value of p instance sees everything the constructor did, and the handoff is fine. So mutexes and atomics are specially known to compilers. And the next question people ask is, well, what if I'm calling some opaque function? I don't know if it's using mutexes or atomics. Then the compiler's not allowed to move across it at all. If it can't prove that it's safe to move stuff across it, it has to treat every opaque function call as a full fence. That's the short version. 3-hour version is on channel 9. Ooh. It's Stefan. Remember I said that there are just like a handful of people in the world? Here's one of them. Okay.
I just want to point out that as written, you are paying 2 atomic loads on the success path because return p instance will read again.
Yes.
If you used a plain local variable, you could avoid that. It's not important for practice, but for performance.
So the point is that I deliberately on this slide for simplicity, which you should always write for first, I don't use an extra local variable, so I do a gratuitous reread from p instance, and in particular down here, and yeah, so I do two loads, which compilers can optimize away, and you know who to ask back home to make that happen. You need to talk to somebody named Eric. So are you writing that email while I'm talking? Thank you. So here is correct double-checked locking. This is if you write it by hand. So moving on, here is a slight optimization. This may be slightly faster, as Stefan noted. You can have a local variable, so you only read as, this is called the Stefan optimization. You read once, then you use that temporary variable twice. This saves you a whole whopping atomic read. By the way, in case you're wondering how expensive these things are, atomic stores can have significant overhead. Atomic loads, reads, are very little to no overhead. This is important because you always, always, always want to make reads fast That's really important. There can be some overhead. On ARM in particular, there's quite a bit of overhead. More than on x86, that's a single move instruction. It's the same instruction as the non-atomic load, which is why optimizers love it. So this is a slight optimization. This may be slightly faster. And if you're writing a standard library implementation, I urge you to think about such things because you know you have roughly 1 million customers, and therefore it can matter. In other cases, either one will do. I would be happy doing a code review on either the previous slide or this one. Yes. By the way, it'll be very easier since we are recording all these sessions. If you'd like to ask questions, please queue at the microphones. We have one here, and one here. And I was reminded I was being bad. I should take questions from the microphones because that way we'll get them on the tape as well. So if you'd like to queue up, feel free. And then I'll take hands from there. You can ask it on your way over because you might ask something else. Go ahead and I'll repeat.
So I just had a simple question. Isn't acquire a stronger guarantee than you need there for the load?
Is acquire a stronger guarantee than you need? See the atomic weapons talk.
Okay.
If you are asking that kind of question and actually know exactly what to do with the answer, you are in a very elite group of people in the world.
Okay, but the answer is yes, right? For this. Because you would need consume, not acquire there, right? I mean, consume would be acceptable instead of acquire.
Consume, well, essentially doesn't work. It's not well specified in the standard. We just were arguing about it on Thursday and Friday at the concurrency meeting last week. So consume definitely, I don't claim to know anything about. I refuse to use, and I don't think anybody, I think that's an even more elite group of people who even know to use that. We're going to continue on the mainstream. Acquire is what you want here, and that in fact is the default that you get.
Okay.
Yeah.
Thank you.
So even better, there is a tool for doing this kind of general purpose work. And in particular, it's this once flag that lets you call once. So here I'm going to have this once flag. I'm going to call once with that flag, and I can do arbitrary amounts of work. And now the standard provides you a way to automatically do this only one time. And it does something equivalent to double-check locking. It actually does something that's even more efficient, probably. Thank you to Google for contributing that piece of work, that algorithm, to the standard. But the most important thing I want to point out about this code is, you notice I've been writing in green the code that actually does stuff. And in blue, the code that is scaffolding you had to do to beat the compiler over the head to actually do what you wanted. There is less of the scaffolding and more actual code. There's no raw pointer here. You get automatic cleanup and less boilerplate, which is a good thing. Finally, you can get that blue code down to one word in this particular case because there's an even more special purpose tool for that. STL likes to call them magic statics. They're thread-safe initialized function local statics. The standard now requires that those which are by default, they're designed to be initialized the first time control passes through them on any thread. We do double-check locking or something equivalent under the covers for you. You simply say static widget instance. You are guaranteed that will be executed once and only once. If two threads come in at the same time, they won't. One will be before the other. They will be synchronized. It'll be initialized once, and you can just return the reference and you're done. Scott was happy about that because he published that years ago, and it works just fine in concurrent code. Questions on the? Yeah. So those are the tools for double-check locking.
Which compilers support this thread local static by default?
I believe the major ones, so Microsoft's GNU, Clang.
All the latest versions?
The latest versions, yeah. Get anything 5 years old and it won't work very well. Okay. In fact, with ours, I don't remember whether it's in our VS 2013 RTM from last fall or whether it's in a CTP or an update since then. In a CTP, okay.
This has been thread safe since GCC 3.4.
So this has been thread safe in GCC since GCC 3.4.
Yeah,
That's wonderful.
Which was GCC 3.4 was released about 10 years ago.
Which is great. That's long before the standard said it should. So I have a deal to make with you here. At this rate, we will get through the advertised material. I'm happy to take questions, and I encourage them, so I'm not discouraging them at all, but some audiences have different appetites. If you want to go really deep on very small details of a particular line of code, that can be interesting, but it'll go beyond the actual meaning of the code, the basic meaning of the code and the point being made, and we'll just take longer on each one. Or we can get to the bonus material. So think about that when you're asking a question, is this really germane to the point being made? And then we can see especially how to use these atomics well to get scalability, throughput. And I've got some performance examples at the end that I think you'll find interesting. So now let's go to locks and atomics in combination. The key requirement is not that you use the same kind of synchronization for every object, but that you do it at every given point in time. So for example, in a handoff situation, if for part of the object's lifetime, it's going to be owned by this subsystem, and it's going to be shared and mutable, well then you have to control access to it somehow. Maybe this subsystem uses a mutex. Perfectly fine choice. Maybe hopefully it's in a lock hierarchy and so forth. But then you may pass ownership over to another subsystem or to a second phase of processing where now these guys, if they're going to share it, which may include some of the previous guys, they have to also control access to it, synchronize access to it, right? They don't have to use the same mutex. As long as everybody at every given point in time agrees, now we're using the mutex, now we switch to a new phase, now we're using atomics or something, you're good. The key is, in an object's lifetime, at any given point in time, everybody agrees on how we're synchronizing access to the object, otherwise the world will fall over. But that doesn't mean you can't use mutexes for a while and then switch in a new phase of processing, a new data structure, to use something else, and that's often desirable, and we're going to see some examples here. So consider this producer-consumer relationship where we have one producer, many consumers. The producer does this. While there's more tasks, he's going to go and create the information to build the task, might be some graph of objects. Then he is going to push that task into a queue. Let's say task is just a pointer to the root of this tree of objects. We're going to take the mutex that protects that queue, push the task into the queue, release the mutex. There's a condition variable here because that allows better sleeping. You can look that up, it's on CPP reference. And to notify it, that's whoever's waiting that there's something new to look at, they can wake up and look. And then we go and we build another task. And once we've built it, again, we take the mutex, push it in the queue, release the mutex that protects the queue, and we keep doing this until we're done. And then we execute that last block just once. We take the mutex one last time, push in a sentinel, saying, we're done, everybody can go home now, release the lock, and notify. So if you look at the critical regions here. So I'm illustrating these as sort of acquire release fences. If you're familiar with what those are the black bars. Those black bars say you can't move across this from the yellow area. So you can't move up across the lock guard, you can't move down across the CV notify. And the yellow stripe that has the bar at the top, that's an acquire fence, so that you're entering a critical region, you're acquiring exclusivity, and then the opposite one, you release it. So here we acquire the mutex, that's acquiring exclusivity, then we release it in two stages. We release the mutex and notify, and then each time through the loop, and then we do it again. Now let's talk about the consumers. The consumer is, there's many of these, they're going to pull stuff off the queue. So they're going to take a lock on the queue. While it's empty, cv.wait mutex. I'm not going to explain condition variables here, you can look them up, but the basic idea is you'll almost always see condition variable wait in a while loop. Because what you're going to do is you're taking the lock once, then you're seeing, is the world in the state that I care about? Is the protected shared state what I care about? In this case, is there something there to consume? If not, what wait does is it releases the lock, that's why you pass mutex as a parameter. It then sleeps instead of spinning, so it doesn't consume resources, it sleeps until somebody notifies it, that's why we're notifying in the producer. Then it wakes up, reacquires the lock, and returns. Now, of course, doing this once might not be enough. If you acquire the lock once, then the queue is empty, and then you do this wait, and then you wake up again, it doesn't mean the queue's not empty. You have to check again. Okay, is the queue empty now? If the queue is still empty, we have to sleep again, until finally we get a notification and there's actually something there, and then we go through and we do all of our work. And in particular, notice that the lock guard ends here. So when there's something in the queue, we'll get the first element, and if my task doesn't equal done, we'll pop from the queue. We just leave the sentinel there for other people to see. And if it's not the sentinel, we'll take it. We release exclusivity, and then we do our work. This is an important pattern. We do our work outside the critical region. So this work here, if you look at where it lives, it's outside that critical region. One of the goals you'll want to do for scalability is make your critical region as small as possible, because the longer your critical region, the more you're interfering with somebody, potentially, who's trying to get work done. That's the definition of not being scalable. So that's a simple example using a mutex, nothing lock-free about it yet. But where do those invariants have to hold again? Just remember, the invariants protecting that shared state, they have to hold here, here, and anytime you enter or leave a critical region, you must reestablish the invariants. The good news is, in that first little critical region where we check to see is it empty, if we then said, oh, it's empty, and release the mutex, we haven't changed anything. So that one's easy. But if you did make any change, you have to put the world in a consistent state before you release the mutex and wait again. A small thing to remember, but always make sure that you know exactly where your critical region's boundaries are when you acquire or release exclusivity, because your invariants have to hold. When you release, you must have reestablished your invariants again, because the poor next guy's going to come along who gets exclusivity and expects to see a sane state. So just make sure you leave things tidy for him. We talked about some of this. Why do we not just mutex unlock? It's because we're optimizing this so that consumers can sleep. We're using a condition variable, so we notify them they can sleep efficiently and then be woken up. And could we make the unlock and notify a single operation? Yes, I really hope somebody someday just merges condition variables and mutexes. There should be a single abstraction instead of two separate ones that you cobble together, but there's not enough time in the world to write up all the proposals you care about. I hope someone does this, maybe somebody in this room. Now let's talk about a sketch. This is just a sketch of using locks and lock-free. So I'm pointing out using locks and atomics together. The way we're going to do it is, again, this idea of lifetimes. There's these handoffs where we use an atomic variable, the handoff from the producer to the consumers, and then we use a mutex as usual. So we're sort of in this halfway state, and then we'll get to a fully lock-free example. But this is to show how you can use them together. What the producer does is he builds his task list. He does all the work he needs to do. So instead of actually publishing one item at a time like before, he's going to build all of the tasks there are to do and then publish them with a single atomic write. Makes the head visible, and suddenly, from the consumer's point of view, all the tasks there are spring into existence. They couldn't see them before, and suddenly, atomically, they can see them all, and then they can go and fight over them. They can go take tasks. But now there's many consumers. How do we make sure that the consumers coordinate among themselves? The consumers coordinate using a mutex. So if you look at where the regions are, here's a critical region for the consumers where we acquire exclusivity to keep other consumers from modifying the queue while we're popping an element. So we pop an element, we let go, and then out of the critical section we use it. But then, notice we have this release here where we go from nothing visible to everything visible. We do that phase of handoff from the first epoch of processing to the second one. We do it with an atomic write. And then we use a mutex in the second epoch, or the second phase of processing. That's just an example to help us to see how you can combine them. But I know you've been waiting for, how do I use just atomics, right? So let's talk about that. I really like this lock-free mail slots example. And the best way to describe this is with a state machine. Imagine that you are in a post office where there is a producer on one side, all the consumers who are looking for the mail on the other side, and in between them, dividing them down the middle of the room, is a wall with pigeonholes in it. So all your mail slots. Now, when you come to check your mail, you look in just your slot, I hope. And that's the legal way to do it, is you look in just your own slot. If there's something there, great, you take it, and you do this periodically. Well, on the producer side, what does he do? He's going through and, oh, look, there's mail. Oh, let's see, I'll put some in for this slot, I'll put some in for this slot. And so now think of those slots as shared state, where for each slot, the producer takes the system, takes the state of the slot from empty to it's either got a task or a sentinel in it. So if it's empty, he'll put something in it. But if it's not empty, he'll leave it alone. It's only if it's empty will the producer put a new task in the slot. And the consumer who's coming along, he will look in his slot, and if there's something in it, then he has ownership of it. He will then take that task out of the slot, and so he owns the transition from having a task in it back to empty. Producers put things in when it's empty. When it's empty, the producer owns it. When it's not empty, the consumer owns it. It's the way to think about it. So let's look at some code. I'm the producer, so I'm now we're getting a concurrency among the task building now. As I create a task, I'm going to assign it to somebody. So I'm going to keep building tasks. While there are more tasks, I'm going to go allocate and build a new one. Now, once it's built, I have to give it to somebody. Who do I give it to? Well, I'm just going to keep an index of the current slot and say, well, is that one empty? Well, if that one isn't empty, and this is an atomic read because the slots are atomic variables, if it's not empty, that means, well, he's already got something. So I'll go to the next one. Is that one empty? No. Is that one empty? No. And finally, he finds one. Is that one empty? Yes. Aha, I found an empty slot. He stuffs the task in that, goes away. Builds the next task, goes back. Is this slot empty? No. Is this slot empty? No. Oh, look, there's an empty one. Stuffs it in. And he keeps doing this until finally he runs out of tasks. And then in phase 2, he basically sticks a done message, a note, you can go home now, there's no more ever coming, in every slot, but he waits to see again, is this slot empty? Yes, I'll stick the done message. So that'll be the next task, will be the sentinel that he puts one in each slot, but he just waits for the slot to be empty because it can only hold one thing at a time. So that's the producer. Make a new task, find the next empty slot and stuff it in. When we're all done, keep going until you put a sentinel in each empty slot. If you do that once for each slot, you're done. And then everybody's notified, the producer can go home. Any questions about the meaning of that code? The algorithm the producer is using? Okay. The consumer is easier. And well, first of all, here are the critical sections to think about. The producer is really looking for an empty slot, right? Why? Because empty means that he owns it. He gets to manipulate that slot, which is to put something in it. So he acquires exclusivity on that slot as soon as he sees that it's empty. That is why we often talk about loads or reads as an acquire operation. I'm acquiring a value, and the special value says, it's my turn. It's just like you look at a mutex, a spin lock variable that says, okay, is it free? Great, then it's my turn if I can change it to be my thread ID, something like that. And then we release by putting the task in, and then notice there's one thing I didn't describe. In each slot is a little bell. That's that semaphore, kind of like the condition variable. He puts the task in, and then rings a little bell, ding, and then the consumer will know it's time to look for something new in his slot.
Yeah,
Question?
My question is, the model I've often used to produce a consumer for queues, whereas you have essentially a continuous stream of events. There is no there's a beginning, but there's no end, essentially. And so and you have one producer, one consumer. So the consumer is always reading the next event, and the producer is always producing the next event, and there's no defined end to it. So how does that work with this? Because there's like
So the question is, what if you're constantly producing and there's no end, you're just constantly doing it, you're in a steady state, especially if it's one producer, one consumer. Well, if it's one producer, one consumer, usually instead of this, you would just use a bounded queue and be done. But in this particular case, if you keep on going with the one producer, multiple consumers, you just drop phase 2. I mean, you just never get to phase 2.
You never just put the done in.
Yes. But now the question is about, especially if you have consumers and producers running at different speeds, wait for it.
Yeah.
We're about to go there. We're about to go there. I have a question for you. Is this algorithm as shown, is it wait-free, lock-free, or obstruction-free? I heard not only groans, but like eyes that went all white and kind of rolled a bit. I know this is a hard question after lunch. Yes?
I believe it's lock-free.
Lock-free? Uh-huh. And why lock-free?
Because the threads can get a bit jammed if all the mailboxes are full.
Exactly. The threads can get jammed. They may wait if all mailboxes are full. So I will say that it is wait-free up to K active workers, which is exactly what you said. Beyond K active workers, so if they're actually, if all the slots are full, then it's no longer wait-free, then it's just lock-free. So overall, it's just lock-free. But if you always know your steady state is going to be not everybody full, you can say at least, well, wait-free up till that limit at least. That gives you an idea of scalability. It puts a bound on the scalability of your system for a number of cores, a number of slots, for example. Phase 2 is merely obstruction-free, because it's only guaranteed to make progress in isolation. Now, here is the consumer code, much simpler. As a consumer, while I'm not looking at the Sentinel, I haven't received the Sentinel, I'm going to look in my slot. Now, again, I read from my slot. I mentioned the variable slot, my slot. That's a read from that atomic variable. If there is nothing there, then I'm going to wait on the semaphore. Just wait for the bell to ring. And so I'm going to go read a magazine or whatever. When I hear the bell ring, the bell that is my pitch, it's my ringtone, all right, then I go look, and then it says, you have mail. So I take out my task. I know that's such an old AOL joke. Yeah, and those of you who just laughed know how old you are. So, or saw it on YouTube. So then I take my task, and in that atomically taking my task, I have read the task, and I set the slot of my slot to null. Make sure it's empty. That way the producer knows that it's available to have something put in it again in a moment. And then I do my work off to the side. Now notice the critical regions here. I am acquiring non-null. That is, I'm waiting until my slot is not null. That means I own it, and I can freely read from it. I read from it, I've got my value. And then I release the exclusivity and allow the producer to do something more with it by setting it to null. Null means he owns it, non-null means I own it. Okay? Why is it a good practice, that last comment, to prefer to do the do work of my task in that location? Scalability. Why scalability? Maybe this side of the room. You've been really quiet.
Just starve the producer from being able to do anything else.
You'd starve the producer from doing anything else. Why? Because even though you've already taken the work and you're doing it, but you've left your mailbox full. You can't jam any, well, it's not like the post office where they jam in mail anyway, but whether it fits or not, it's okay for magazines, but not for Amazon shipments. And you're jamming him up where he might now be spinning because he's got a task all dressed up, nowhere to go. And really, you could have released that slot and have him queue up the next task. The other reason is because as a consumer, if I set that to null right away, I get better utilization of the consumer because it means as I now do my work, it could be that another task might arrive. So not only have I unblocked the producer because there's now a place for him to put the next task, but it's better utilization for me because when I finish my current task, then I can look immediately without blocking, without suspending, see there's something, pick it up, and immediately continue. Otherwise, I need to sleep, and that can be an expensive thing. So I can keep on going get better utilization, right? Any questions about that so far until I put probably the most subtle question of the 2 hours in front of you?
I have one about that.
Please go to the mic while we're going over here. Yes, at the mic.
You made that argument about throughput, which I think makes sense, but aren't you potentially trading some latency for that? That because the producer might put something in a slot of a worker who's not going to be free for a little while, where there could be another worker who actually is free right now?
So it could be that I'm trading off throughput and latency. So we're worried so much about our poor producer friend here that what would happen if I just left that item in the slot longer? in a sentence, in a nutshell? If I left the item in the slot longer, if I swapped these two lines, that's the next question.
Yes.
What could happen? Maybe you've anticipated my hardest, subtlest question.
The producer, and he would stick it in someone else's slot unless all of them are full.
Yeah, so if all of them are
Like the
full,
producer
that's no
spins.
good, but maybe he'll stick it in somebody else's slot. That's true. Peter, any observations on this specific question?
Yeah, I was asking why the freeing of the slot is in the conditional and not in general.
Why the freeing of the slot is in the conditional.
So when you're done, why don't you free your slot anyway?
So you're saying why not just put the slot equals null down at the end, say?
No, before
Because-
the if.
Because the producer has keeps account of how many people he's notified as done, and he might notify you twice. You're done,
Yes.
and then you're done again, and then.
Yes. So the producer counts how many people he's notified to go done. If he notifies you twice, then he's not going to notify somebody else, and you don't want to pay for that overtime. Yes.
Thank you.
So now let me ask this question. Under what circumstances could it make sense to swap those two lines? Now, those two lines are in the right default order. I want you to just automatically, without thinking too hard about it, put work outside critical sections. That's almost always the right thing to do. But there's that word almost, and there was he disappeared. That makes you next.
I'm going to guess that if the producer is a lot slower than the consumer.
Elaborate. Nicely put.
If the producer takes more time to produce new tasks than the consumer takes to finish them.
Excellent. How many of you think that you can pretty confidently reason about which order to put those two lines in? Not even the person who just made the comment. Okay. Think about it this way. Actually, usually this takes a few extra minutes as we talk about options, but you actually went right to the key thing. The key question is who runs faster? The producer or all the consumers? Another way to say the same thing is, what is the normal state of the set of mail slots? If you were to walk into the post office as a random customer who's not involved in this process and just look at it, at what's going on, do you normally see slots where some are empty? Or do you normally see them all full? If you normally see them all full, what do you want to do? Which order should the lines be in? As written. If you see that there's usually an empty slot, which order do you want to put the lines in? The opposite. Why? Because if you take your task out of your slot, you make yourself available for another task while you're busy, you might get assigned another task, which is great for your utilization, you selfish person. But what about your friend who's been sitting there reading a magazine just waiting for work to do and he doesn't get it even though he's free? Right? So think about this. This is really subtle, and it is not something that is obvious in the code, except if somebody writes a comment that you should never delete under maintenance and should always respect. I don't know how you do that with comments, though. Stefan.
Would it make sense possibly to introduce another state? Null, you've got mail, everybody's done, and then I got my mail and I'm still working on it. So the producer could prefer to fill completely empty mailboxes, and as a last resort, if mail keeps coming in and it's getting backed up, then go fill the boxes of people who are working to get a compromise between latency and utilization. Would that work?
Yes.
Okay.
And if you do that, then your mail slot variable is atomic of?
Well, enum, right? Or
And enum.
yeah.
And you need to be it needs to be a bit more than enum, because right now task is probably a pointer.
Yeah.
So your slot is now getting bigger, but yes, you can do those kinds of things. Another kind of thing you can do, especially if the utilization is very lopsided, is to, instead of every slot being an atomic variable, have it be a queue. But that's if it's really lopsided. I'm not going to go far down about how much more can we do, because the purpose of this is to understand this example, is to understand I have just a single atomic variable and be able to reason about how do people share it, how does the length of my critical section and the way that I release critical sections affect scalability, and especially how does it affect workload balancing, in this case between producers and consumers. we want to be sure we grok this example deeply, which usually takes time to go back and think about it over a beer, before embellishing on it. But yes, there are things we can do to embellish on that and turn it into a different algorithm. But I'm focusing on this algorithm.
If you have a particularly expensive...
Closer to the mic?
Sorry. If the consuming is particularly expensive, wouldn't you also want to potentially reverse the order? So you don't have like an expensive resource sitting idle whilst another consumer is consuming one job and already has another one?
That is another way of saying that it's a balance between the producer and the consumer. It's who runs faster, who's more expensive, who don't you want to underutilize.
If the consumers are running slow, you might want to make sure that one consumer can't have two jobs pending.
So there's a lot of optimization you can do. And there are probably another set of a dozen questions like that where you can say, well, what about relative costs? What about throttling? Remember, it always comes down to you're looking for two things: scalability, throughput. I'm going to try very hard to show a concrete example of measuring those in the bonus slides if we get to them. One more, and then we'll keep going.
If the work may fail, and in case it fails, you want to switch the test to maybe another thread or whatever, does it make sense to swap the lines?
If the work may, I don't know, I'd have to think about it. I don't know if just whether the work may fail and then you want to reassign it affects this or not, because the key question here is, do you want to keep other consumers utilized or not if the producer is running fast or slow with respect to them?
Say the do work throws an exception or whatever. I mean, you just lost the task because it's not in the queue anymore. That's basically the point of the question.
So that's mail slots. We're going to keep going now. Actually, we're so close to break. We're so close to break. I'm getting 5-minute cards. The thing is, if we start this, there's a chance after break that we might get to the bonus slides. It's your choice. No pressure.
This is going to be very quick.
Okay.
Okay. You're assuming a steady stream of producers and consumers always running at the same rate. What happens if it changes, that you have a flow and then it stops for a while, then you have another large flow? How do you deal with it? Because you can't reverse the lines after the code's compiled.
The way you reverse the lines after the code's compiled is with an if conditional. But, and no, I'm actually not being snarky, but I'm saying you have to design for that. I mean, that's really easy to say. No, he's exactly right. That's easy to say. It's easy for me to write that if conditional. What's hard is getting the data to say what the conditional should be, is instrumenting it. That's the hard part. So you're exactly right. Again, that would be an embellished algorithm, but it's certainly the kind of thing you can do, because in real systems you do get ebb and flow. In fact, in this idealized example, I'm a mathematician, so everything's a circle and everything's round, right? And frictionless, that's always good. Now, that would be physics. The key thing here is that it's interesting enough to isolate, to analyze a system where there is just one producer and a fixed number of consumers. That's interesting and subtle enough. If we then take away or add consumers, add producers, or they otherwise run at different speeds, because all of those are in another way of saying they run at different speeds, right? Adding more consumers or taking them away is often roughly equivalent to saying they run faster or slower with respect to the producer. And so some of the reasoning boils down to the same thing. But if you get this ebb and flow, then you probably want to measure it, have some heuristics, and adapt to it. Let me introduce the third example. It'll give you something to think about as you grab a quick caffeine boost. Here's an example of a singly linked list. How many of you have written a singly linked list? Don't lie. Okay, it's funny, I saw a certain number of hands going up, and then as soon as I just said the don't lie, like double the number started going up. It was really interesting. It was like two waves. It's like, oh, okay, all right, I did it. Certainly, I come from a C programming background back in the day, in the 80s, early 90s, where there's no standard linked list in the C library. So what do? Almost the first thing you do on a new project is write your own, or take your floppy, remember floppies? And not USB sticks, my friend, floppies, from your last job. And use the one you wrote for them, or use the one that's already in the system. So we've all written these singly linked lists. It's so easy. We do it in our first couple of hours at a new job as C programmers. And in fact, I'm going to make it simpler. There's only 4 operations I want you to support for this linked list. Construct it, destroy it. Those ones are easy, by the way. They do not require synchronization because you always assume you're isolated. There's no other threads running while you're constructing or destroying. It would be a programming error to use something while it's being destroyed. So you can assume the caller gets that right. So the only 2 interesting operations are find and insert at front, push front. Challenge, write a lock-free implementation that looks roughly like that callers can just call find and push front as much as they want without any external synchronization. All the synchronization is internal. You don't use locks, you use atomics. Think about that over break. Let's come back in 15 minutes and we'll consider it.